Let us consider the example. Over here, we have been given the source program and we are required to perform pass 1 of a 2-pass assembler. So essentially, we are required to show the contents of symbol table, literal table and pool table at the end of the pass 1, and at the same time we are required to show the intermediate code generated or intermediate representation of the code of variant 1. So students, in the pass 1 of a 2-pass assembler, we pass the input program and we produce the data structures like symbol table, literal table and pool table. Okay, so these are the tables that we generate by the end of the pass 1. Along with this, we translate or we change the form of this input program into some intermediate form and we refer it as intermediate code, that is in short IC. Now this intermediate code is of two variants, that is variant 1 and variant 2. Okay, so in the question we have been asked to show the intermediate code generated for this program of variant 1. Okay, variant 1 and variant 2 in detail we will talk shortly, but right now we will be focusing more on the variant 1 as we are expected to generate the intermediate code in variant 1 only. Okay, so once this program is being given to the assembler pass 1, assembler pass 1 will start parsing input program. Now before parsing the input program, we need to know the syntax of the program being written or the instructions being written in the program. So initially we are going to find a label in the instruction, which is the optional one. So I will just try to put it in square bracket, means it's optional, followed by the opcode, that is the instruction. This is going to be the compulsory field. Next is operand 1 and another field is operand 2. Now this operand 2 field is again optional. It's not applicable for all types of instructions, that is specifically imperative statements. Now while parsing our program, either in the beginning we are going to get something against the label field, or in case label is not present, it is obvious we are going to get something which will be referred as the output. Okay, so the anything that we are going to find against a label field, let us assume over here in this instruction we are getting L1, which is considered as a label. So it is obvious whatever we are going to get against the label field is going to be the symbol. Always it is going to be a symbol. Okay, now uh, let us move to the pass 1 of a 2-pass assembler. Now first instruction is start 201. It has no label. Okay, so whatever we are getting is start, which is the opcode, and it is of type assembler directive. Okay, so assembler directive start 201, it denotes, it asks the assembler to start generating the target code from location 201. So over here the location counter is set to 201 and by default the location counter is set to 0. In case if we do not have the operand to the start instruction, that is in case if we do not have this operand, in that case the assembler will start generating target code from address 0. Okay, but in this example, over here we have been asked or the assembler have been asked to start generating target code from location 201. So this 0 will be overwritten by 201. So currently our location counter is pointing to the location 201, and as it is the assembler directive, this is the assembler directive type of instruction, we do not perform LC processing over here. Okay, so hence we will not have the address over here against the LC field for this instruction start. So remember students, we will be performing the LC, that is location counter processing, against only imperative statements. Okay, and for declaration statements as well, but the use of declaration statement is different. As we progress through the example, I will try to explain you how we will be processing the location counter for the instructions corresponding to declaration statements. Okay, now the LC is set to 201 and our first line is processed. So this is the assembler directive which instructs assembler to start generating target code from 201. So assembler updates the LC by the value specified in the operand field of the start. Now moving to the next instruction, again it doesn't have anything against the label field. So whatever we are going to get is going to be the opcode, and the opcode is move R. This move R is of type imperative statement that we will get to know referring to the OP table or OP tab, machine opcode table. So in the machine opcode table, from the list of all the opcodes that we have in the OP tab, we will be getting the move R instruction of type imperative statement. Okay, as we discussed, for imperative statements we will be performing location counter processing. So for this particular instruction, the location counter will be set as the current value, that's 201, and as we know in the OP tab, the third field was the length of the instruction, and I have already told you that we are considering the length of each imperative statement as 1, as it is a hypothetical language. It may vary depending on the type of architecture we have, but over here for the sake of understanding we are considering the length as by default 1. So the location counter for this instruction is going to be 201, and as its length is 1, so we will increment LC by 1, so the LC will be updated to 202. So by the end of this particular instruction, our LC will be changed to 201. Now similarly, moving to the next instruction, move M. Again, if we see in the OP tab, we will find move M instruction in the of the category imperative statement, again considering length as 1. So the current LC is 202, which will be given to this particular instruction, and again increment it by the length of the instruction, which is 1. So LC will be set to 203. Okay, so this is how we will be carrying out the location counter processing. Now let us assume a situation where we have another assembler directive. So over here origin, which is an assembler directive. So if you see, we have not written the location counter or any address over here. Okay, similarly LTRG, which is of type assembler directive, again we do not have the location counter over here. Okay, so basically location counter denotes the address or the location where this particular instruction is being stored or loaded. Okay, so for this particular instruction, the location counter 201 means at location 201 we have loaded this move R instruction. Okay, Similarly, at location 202, we have loaded this move m instruction, and similarly 203 move m again, so on and so forth. Okay, but for the assembler directives like origin or LTORG, we have not specified any location over here. It means we are not going to load any of the assembler directives in a intermediate code, okay, or in the memory. Okay, why? Because assembler directives task is just to instruct the assembler to do something. Okay, so this is how the location counter processing is done. Specifically for declaration type of statements, if you see this instruction, okay, this is declare storage of this instruction is of type DL, okay, and if you see the particular instruction DS is being given the location counter 215, so it means that this symbol X, which is present in the DS instruction in the label field, so this X is defined over here, and this X was being used throughout the program. Okay, so over here this occurrence of X in the beginning, it was a forward reference. Okay, forward reference means at this point of time the X was not being defined or declared what this exactly X is, rather it was used in the move M instruction as its operand. Okay, so the definition of this X is encountered over here in the DS instruction, that is declare storage, and for this particular X the storage of one memory unit is declared, and that particular memory location is 250. So it means X is pointing to the memory location 215, and as this operand of the DS instruction is 1, it means only one memory unit memory location is declared for this symbol X. Now let us consider another example where we have uh, let us assume X DS 4, okay, and the current LC is, let us assume, 210. Okay, so it means X is pointing to the location 214, and for X total 4 memory locations are reserved starting from 210. So 210, 211, 212 and 230. So these are the 4 memory locations are declared for the symbol X, and X will be pointing to the first symbol, that is 210. Okay, so this example I have stated only because in case if we wish to update the location counter, which is currently 210 by the end of this instruction, this is going to be, or this is going to be incremented by the operand that we have in the DS instruction, that is 4. So the next LC will be 210 plus the operand 4, that is 214. Okay, okay. Now in the example, the operand of the declare storage instruction was 1 and the current LC was 215. So the next LC is going to be 215 plus this operand 1, that is 260. Okay. Now we are aware about the location counter processing, basically how this location counter processing is done. Okay, now next is how we will be generating the intermediate code as well as the tables that we generate as an output of the Passman, that is symbol table, literal table and pool table. Okay, so these are the tables that we will be generating, and intermediate code of variant 1, this is what we will be generating as output of Passman. So if you see the intermediate code over here of variant 1, so in the variant 1 what we do is we try to translate or we try to transform all the instructions and all the opcodes of these operands of these instructions into some intermediate form. Okay, so everything we try to translate into some other form. This is what the variant 1 is. Okay, in the variant 1, for now, let us just assume we won't be translating each and everything. Like, let us assume in this particular variant 1, this move R instruction has the uh, A register as its first operand. So if you see in the corresponding intermediate representation, that is of variant 1, we have translated it into 1, or we changed the A register to be written as A register straight away. Rather, we tried to write it in some other form, that is 1. Okay, so in the variant 2, let us assume registers are not to be translated, so we will try to keep a register or all the register occurrences as it is. Okay, so that is just the basic difference. Further, we will try to look at one of the examples using variant 2 as well, but right now we will try to focus on the variant 1 only. Now let us say, go through the example. So the first instruction is start, which is of assembler directive type. So hence we do not have any LC. So hence no LC. Now, as start is assembler directive, we will try to replace start by AD comma 01, referring to the OP tab. Okay. So if you uh, see the OP tab, let me show you the OP tab. Just a minute. Okay, so if you look at this OP tab, that is machine opcode table, the start instruction, if we wish to locate, we will find start instruction over here. And if you look at the class, its class is assembler directive, and the mnemonic info is 01. So instead of start, we will be write it in some other form as AD comma its mnemonic info, that is 01. Okay, now let us assume another example. In case in our program, if we get instruction sub, so we will try to write it in some intermediate form as its class, that is imperative statements, that is is, comma its mnemonic info, that is 02. So essentially this will let assembler know the particular instruction is of imperative statement type, and its mnemonic info 2 will locate that particular instruction, that is sub. Okay, so this is how the instruction is being translated into some other form.